Hi everybody. We'll talk today about the last thing in this chapter. We'll talk about the work and power. We know from before the work and power, work in joules, power in watts, but we will talk about them in rotational motion. Also, we'll talk about the momentum, which is a mass multiplied by velocity. But this velocity is angular, and this is an angular momentum. We have also a collision in rotational motion. We will see that. And we will see that the angular momentum will be conserved. And we have two cases, elastic and inelastic collisions. It's the same. Just put your mind in rotational motion. And we will do that by doing an example. We'll cover everything we learned. Okay, I'll remove everything down. Okay. Now, work and power in rotational motion. If we have a motion, and this motion is linear, we have a force, and we have a distance, which is delta x. We know that the work is F delta x cosine theta. And theta in this case is 0, and cosine 0 is 1. We know that. If we have a rotational motion, and we have a mass, and this mass is moving. Okay? And we have a radius for this motion, which is r. The motion of this mass is, we know from before that the circumference of the circle is s equal to 2 pi r, where this is r, right? But if we take just a part from this total circle, this will be the s, and the total angle is 2 pi multiplied by r. But when we deal with d theta or delta theta, it is a part of that total 2 pi. Then we have ds, and this ds is the angle d theta or delta theta, if you want, if you need, multiplied by the r, the radius. Okay, our mass now is moving delta s, or in work language, it is delta x, right? And if we divide this curvature or this curve to small pieces, we can imagine that this small piece just like a straight line. It is just like delta x or dx. It is a straight. For example, when we look at the Earth's surface, the Earth is a sphere, not flat, okay? The Earth is a sphere, but when we look at our small distance, we see it is a straight, right? And we can now define the motion of this object, the displacement, delta x, okay? And this motion is because we have a force. Okay, now we have the work as known is equal to the force multiplied by delta x or delta s. The force in the same direction of delta x. So we have cosine 0, it is 1. Okay, where is r? We are dealing now with the force and with the displacement. We don't have r. but the displacement, it is ds, it is equal to d theta multiplied by r. Now I can remove this, and this is 1, and put the place of delta s x, it is r d theta multiplied by f, which is equal to the same force, to the same work in joules. Now, r multiplied by f, we know that it is the torque. D theta is delta theta, or d theta. This is the work for d theta, or small theta, or you can take it as d work. It is a small piece from our work. We need to apply the integration rate, or we need to apply the integration. Now, if we integrate the both sides, then the work is equal to the integration from theta 1 to theta 2 for tau, which is f multiplied by r. R is constant. F is f. There is a person pushing something in a circle. Multiplied by d theta. This will be equal to, the work is equal to tau theta 2 minus theta 1, or delta theta. This is tau, which is the work. Do you remember that the work in linear motion is equal to F multiplied by delta x? It's the same work, but this is linear, and this is no, this is angular, and this is linear, right? By this, we see that we deal with the same thing, but first we talk about the linear motion, and now we are talking about there is a typo here, I think. It is not omega, it is in the sheet, it is not delta omega, it is delta theta. I'm sorry about that. I will fix it and I will upload it again. Okay. If you remember also, when we apply work energy theory, we find that the work is equal to the change in kinetic energy, which is kinetic energy 2 minus kinetic energy 1. And this is equal to half m v2 squared minus half the mass v1 squared. We can apply this for the angular motion by the same way. And any one of you can expect the shape of this relation. This is the work. This is kinetic energy. Kinetic energy. Half is half. I'm moving now to angular motion. What is the place? We need to remove m from linear motion. What we need to put? What is the mass in rotational motion, which is the mass rotational mass effect? It is the moment of inertia. What is v in angular motion? It is omega. It is squared minus half I omega 1 squared. And we can find that from the relation of the work. The work is equal to tau delta theta. Yes. Maybe it was not a typo. Now, the torque from Newton's second law is equal to I multiplied by alpha. Alpha is the angular acceleration multiplied by delta theta. alpha, we know that alpha is delta omega over delta t, or d omega by dt. We know that the acceleration is the differentiation time derivative of the velocity. And this is dt, d theta, this is d theta, this is I, this is equal to the work. Okay? What if we just move? I told you that from before. We can, in physics, move any quantity or any expression anywhere. I will move this to here. It will be dt. So again, now d theta over dt is omega. We have here d omega. Now the work is equal to the moment of inertia multiplied by omega d omega. We need to integrate it again. If we integrate it by integration, this is the work again. Equal to the integration of I from omega 1 to omega 2. Omega d omega. What is this is equal to? Huh? The work is equal to I, the integration of omega d omega. It is omega squared over 2. Right? When we need to integrate x dx, it is equal to x squared over 2. Right? Now we integrate omega d omega. It's omega squared over 2 from omega 1 to omega 2. Okay, so the work is equal to half I omega 2 squared minus half I omega 1 squared. It is just like what I told you from before, and you can expect that because that's enough. Now we know the mass is I, the velocity is omega, the x is theta, the acceleration is alpha, and so on. Right. This is the work, energy, theory, and rotational motion, right? It is just like what we talked from before. Now, it is simple to find the power. Power is equal to the work divided over delta time period, right? It is in what? This is in joule. Okay. The work now in rotational motion, we don't need to compare it with the linear motion now. The work is tau multiplied by delta theta, yes, over delta t. It is the power. Delta theta over delta t again, tau multiplied by omega. The power from before is equal to the work, which is x, the force multiplied by delta x over delta t, which is equal. Delta x over delta t is the velocity, and this is f. We have dot product between them. It is the same. Any question about that now? Any question? Online questions? Okay. Now I will solve an example. We have this game in the, I don't know the name of it. Sorry about that. We have this, and we have a mass hang here. This is a mass. You know the name of this game. And it is rotating by angular velocity omega. And the mass is given, it is 1,000 kilogram, I think. Total with the people inside the cabinet. And the radius are 6 meters. And we have omega. Look at omega now. Omega is equal to 2 pi over 60 radians per second. I put it here like this to be understood. Omega is an angular velocity. Okay? It is 2 pi. 2 pi means total rotation during 60 seconds. 2 pi radians total rotation. 60 seconds mean total rotation 1 round during a minute. Okay? I didn't put it as a number, pure number. I put it like this to know, we can imagine the velocity of this machine. Now, we need to find 4 things. Okay, we need to find the torque affected by the engine. We have an engine here, a motor or something like that. Rotate the system. How can we find the torque? We know that the work is equal to, we have many relations, but we need to use today's relations, okay? The work is equal to the torque multiplied by delta theta, yes? We need the torque done to move the cabinet from this point, which is at the bottom, to this point. How much delta theta for this motion? I'm asking now. How much delta theta? I will not talk anything. How much delta theta? I need to hear it. Why pi? Because we have 2 pi. Now this is half around. So this is just pi. This is the circle. This is 2 pi. Now we have just this is 2 pi. Now we have just half 2 pi. So delta theta is just 1 pi. The torque is unknown. The work is unknown. This is the first requirement. If now I cannot solve this equation, I need to go to the second requirement. What is the work? Yes. What is the work? Compute the work done to lift this mass from here to here. Who can tell me? You can see that in the sheets. If this is mass equal to 1,000 kilograms. Okay. And we need to lift it to this point and this point. We know from before that the work is equal to the positive change in kinetic energy, and it is equal to the negative change in potential energy. Right? But this is the work for gravity. Now I'm asking about the work done against that change in potential energy. I'm asking about the work done by the engine. Because the potential energy done or the work done by gravity is negative delta U, then the engine need to do this work, which is positive delta U. I'm asking now about the work done by the engine, not by the gravity. Previously, we put minus sign because we were talking about the gravity. Now we are talking about the engine. So, if you look at the mass between the initial point and the final point, how much the change in potential energy? The change in potential energy is equal to U2 minus U1, which is equal to this is the point 1, this is the point 2. U2, it is mgh2 minus mgh1. Am I right? Okay. How much H1? 0. So the initial potential energy is 0 because H1 is 0. How much? The mass is 1000. G is G. How much H2? The radius is 6. How much H2? This is H2. We have 6 with 6. It is 12, right? So the change in potential energy is equal to the mass, which is 1000, multiplied by G, which is 9.8, multiplied by the altitude, which is 12. This is equal to this number, okay? Now, we have a mass at this point as 0 joule. It is full. Now, finally, we have this mass here with 117,600 joules. So it is rich now. From where these joules come? They come from the engine work. So the work done by the engine is equal to this amount. So anyone? So the work done by the engine is equal to delta U, which is 117,600 joules. Do you agree with that? Is it logical? Now, go back to that first. We can find tau. The torque now is equal to the work divided over pi, just like that, which is equal to 100,000, 17,600 over pi. Pi, simply, it is a 3.14. It is a number, okay? And this torque is equal to 37. 433.24. What is the unit of the torque? Newton meter, because R multiplied by the force. It is not joule, okay? The torque is not an energy. This is the first and the second requirement. We just apply the formulas. Okay, what is the next? We need the power. Now it is simple. The power, I think we can find it by two ways. The power is equal to the work done divided delta T. And it is also equal to the torque multiplied by, this is omega, by omega. Okay. Now the power, the first way, power is equal to tau multiplied by omega. Tau is found omega as given, it is 2 pi radians by 60 seconds. It is not a, it is rotation during a minute. This will be equal to 3,920 watts. And it will be the same number if we compute the power using W, which is the work. We find the work that was divided over the time. I compute the time at the side. Okay. How much our theta now? It is just one line. How much the time for this theta? For a total rotation, we need 60 seconds. For half rotation, we need 30, the half of the time, right? Right. It is 30 seconds. This will give me the same power in watts. Okay. I'll remove this. As always, you have more discussion about angular rotation and angular momentum in the Canvas page. Not just these sheets, but these are the main sheets for our lecture. Okay, what is the kinetic energy? We need to find the kinetic energy. And I told you, assume that the angular velocity is constant. Okay? This is 1/2. And also I assumed that the cabinet as a point mass. So the moment of inertia will be mr squared multiplied by omega, which is 2 pi over 60. We need to square it. M is 1,000. R is 6. We need to square it again. Now this will give me the kinetic energy. It is 197.3. No, 4. 2. This is the kinetic energy for this rotated mass. Okay. Any question about this line? Okay. I will move now to angular movement. It will not be difficult or complicated. Just we need to multiply it by r. Then we will move from linear to angular motion, as always. Angular momentum. As we know from before, the momentum P is equal to m multiplied by v. What if we need to talk about angular momentum? M, it will be I, V will be omega. But how we will do that? Okay, if we multiply both sides by R, P, it will be M, R, we have V. But V is equal to R omega. And the acceleration is equal to R alpha. We know that. V, it is R omega. We have now mr squared, which is the moment of inertia. And we have omega. Now the angular momentum will not be P, it will be L. It is a vector quantity. The moment of inertia, it is not a vector, but the omega is the vector. Okay? It is simple. Just like that. What else? We need to know the general form of Newton's second law. We know, or we knew that from before. We know that from before that the force is equal to dP by dt as a vector, and it is equal to d by dt to mv. The velocity is a vector. This is the force, the linear force. And we know that if m is a constant, then it will be m dv by dt, which is the acceleration. It's the same now. We have p, which is L, equal to, as a vector, it is equal to the moment of inertia multiplied by omega as a vector. Okay, now, if we derive the both sides with respect to t, will be equal. The moment of inertia is constant, and we have d omega by dt. It is the acceleration, but it is the angular acceleration, which is alpha. So this will be equal to I alpha. That's it. This is the torque. So the torque is equal to the time derivative for the momentum. Just like that, Newton's second law, the general form. Any question about that? Now, we need to look at the vector direction for L, omega, and all of these things. If I am moving this thing, we have omega, which is a rotation, and I am moving counterclockwise, so my omega is positive upward. Do you remember that? The right hand side. This is omega to the z direction. Okay, I am acting by a force on R. R across that force is a torque. It is to the z direction. So I have so my omega is in z direction as a vector. Also, the torque in z direction. Okay, the momentum, the linear momentum is horizontal, but the angular momentum, L, it is to the z direction again. Because, look at here, L is in the direction of omega, and it is in the same direction of alpha. We have alpha now, and it is the same direction of tau. So we have the angular momentum to the z direction and the angular acceleration to the z direction. Note that sometimes if I am moving this fast, then I move it slowly. Then I have negative acceleration, and this negative acceleration is to the negative. If I decrease my velocity, look, I am fast now. I will not throw it. Okay. I am fast, but later I am slow. Then I have negative acceleration and negative alpha. The negative alpha to the negative z direction. When I am talking to you now, all of them in z direction, some of them sometimes that depend on my magnitude, it will be to the negative. But the main direction is along the z direction. The z direction with respect to what? With respect to this plane. To this plane, right? This plane is the plane of the force of R. R across the force, it is this plane, and the z direction is that perpendicular or the normal one of them for on them. Okay. Any question about that? Line. Okay. Now we have time. I will solve a long example, and this example will cover many things. Take it as a review for this lecture, for this chapter, and some of the previous chapter. Also, this example is talking about the conservation of angular momentum. I will remove this. Now, this is 10.6, but it is example. Okay. If we have this machine, what is the name of it? Roller wheel. I don't know it, but just look at an example. And this example, I need it for rotational motion, and I need the mass changing. I need the mass to change during the rotation. You know this disk, and we have many of these disks. For example, if we have a rotated disk, and we have an arrows, and this arrow comes to this disk at this point during the rotation. It is the same problem. If you assume that we have this game, and we have kids, and this game is rotating, and we have kids. One of these kids go out of this rotation. It will increase its rotation speed, and so on. But we will try. We will see another example on Canvas, and you have this example today, and it will be, I think, a comprehensive example. We have a rotated disk with radius r and velocity omega, and it has a mass, capital M. During rotation, there is a ball jump here and settle at this distance. This is capital R. The radius of the disk, capital R. The ball, the small mass, M small, at R small. So we have now capital mass with capital R radius and small mass with small radius. But this comes after the rotation stuff. Okay, now what we need also. Yes, the radius for the disk is 60 centimeters, and its mass is 2 kilograms. I assume it as a disk. And omega, just like the previous example, it is 10 2 pi's during 1 second. Wow. Is it fast? We have 10 2 pi's during a second. That means 10 rotations during a second. Is it fast? It is faster than the previous question. Okay. Assume small ball, the small ball with small mass. It is 0.1 kilograms. Also, the radius of this ball is 50 centimeters, 0.5 meter. Okay, what you need? We need to compute all of these. We have time. Is my system understood? I'm asking all of you, online and offline in class. In physics, we need at first to understand the system. The disk was rotating. Then later, a ball jumped here. So we have interaction. This is a collision, for example, by the way. This is a collision between a zero velocity, angular velocity ball with a rotating disk. Okay, now find the initial angular momentum. I need the angular momentum initially, before the collision, before the interaction. It is equal to, I will not put the vector direction because the disk is horizontal and all of my angular quantities are in z direction, right? It's just like that. The angular momentum to the z direction, the torque to the z direction, the omega to the z direction, all of them. It is equal to the angular momentum for the disk initially plus the angular momentum for the ball initially. I will compute them for this one. Angular momentum for the disk initially is equal to I omega. I for a disk, it is half. Moment of inertia for a disk, it is half, I think. mr squared. Yes. It is half m for the disk, which is capital M, with r squared. Multiplied by omega. So it is equal to half. The mass is 2. R squared, it is 0.6 squared. Multiplied by omega, which is 10. Multiplied by 2 pi over 1 second. There are no squares. Okay? This will be equal, all of this. 22.60 to, what is the unit? The unit is moment of inertia, meter, kilogram, meter square. Omega, it is radian per second. This is the units of angular momentum. Kilogram, meter square, radian per second. Kilogram, meter square, radian per second. It's a long one. What about the angular momentum for the ball? Remember that initially the ball wasn't rotating, right? So it is equal to I omega for the ball initially. The ball is a point mass, So its moment of inertia is equal to R, mr squared. Okay? But omega is 0. It wasn't rotating, it was outside of our system. So the initial angular momentum for the ball is equal to 0 with the instruments. Right? It is just like a mass moving with the velocity. This is a mass m1 and hit another mass, collide with another mass with velocity v0. You remember that? This is a linear motion. This is a rotational motion. It's okay, we know the givens now. I use these chalks because it's better for the video recording. Because the previous one was thin. But this one has more dirt. Okay. Now, what we need to compute later, the final angular momentum. Okay, we have the initial angular momentum and the final angular momentum. I will tell you, the angular momentum, it is just like the momentum. It is conserved. So, the angular momentum later, it is equal to the angular momentum before, which is equal to 22.62 plus 0, which is equal to this number. This is the angular momentum later. It is conserved. Now we can find the velocity later. So the third requirement, we need to find omega 2. Look, now we have the two masses move with the same velocity because the ball is stick at this point because there is a hole, right? Both of them, this is with R and this is with small r. This is capital M, this is small m. And both of them are moving with the same angular velocity omega 2. Okay, how we can find that? It is simple. We have L later is known. It will be equal to L for the disk later plus L for the ball later. Right? We are talking after the collision or the interaction. Our interaction is collision. Okay? Now, we know everything. We can't find anything. This L later. L2 is equal to 22.60 how much? 62 also? Okay, is equal to L for the disk. It is half M capital R capital square multiplied by omega 2, which is equal also and not equal plus I need to add the angular momentum for the small ball, which is M small R squared multiplied by omega 2. They have the same velocity because they are stick together. This is just like the full or total inelastic collision, right? So I can take omega out of them. Omega 2 is equal to these things. Half mr squared plus mr squared. One of them for the ball and the first one for the disk. I will compute this, and you know that this is I for the disk, and this is I for the ball. I will not put or use every time half mr squared, mr squared. I will use just I for the ball and I for the disk. This is the same. This is the mass. This is the rotational effect of the mass. This will be equal to, I computed, I think. I for the disk is 0.36 kilogram meter squared. Okay, and for the ball is equal to 0.025 kilogram meter squared. So I need to use them always. They're just the mass. Okay, I have known thing with known thing, which is 2262 with unknown thing. So omega 2 is equal to this over this and this, which is how much? It will be 0.36 plus 0.025 omega 2. Be careful now. It is just a pure number, 58. We will talk about that. 0.75 radians per second. Look at this now. We are not dealing just with numbers. We are physicists now. We have omega 1 is equal to 10 rotations during a second. Right? If we compute this as a number, it will be 62.83 radians per second. We have now omega 2 is equal to this number, 58.75 radians per second. This will be equal to what? 9.35 2 pies or rotations per second. What can you talk about this or comment? What is your comment? Before the collision, before the small ball, our velocity is 10 rotations. But after the existence of that ball, our velocity is 9.35. It is slower. That is right. Because now we need more energy. And this energy goes to this ball to rotate it. And this kinetic energy is stored or steel from the big disk. So its rotational velocity or angular velocity comes to be slower, right? But the angular momentum is conserved. The velocity comes slower after the collision. We know that again and again. When we have a linear collision, if we have a bullet with velocity 400 meters per second, and it sticks inside a box, and this box, a wooden block, was stationary before the collision. After the collision, their velocity, maybe it is half meter per second. The velocity going down because we have an additional mass. in our system. We have here the same thing. We have a rotated disc. I'm talking a lot, I'm sorry for that. But I learned that from my Yarmouth University. Okay, now we have a rotated disc with this velocity. After the collision, the two masses stick together and the velocity comes slow. Any question about that online? Okay. Now I will compute another thing. I will compute the new velocity and the new angular momentum for both of them, for the ball and for the disc. It's a simple, comes away directly. So L2 for the disc is equal to I for the disc. I will not write this expression again. I2 multiplied by omega 2. Omega 2 is this, which is the same for both of them. I is known, 36%. This will be equal to 21.15 kilogram meter square radian per second. You need to name it something. Okay. Also, for the ball, assume muted, please. Now, we need to compute the angular momentum for the ball. It is equal to the moment of inertia for the ball multiplied by the same omega, which is omega 2. The moment of inertia is 0.255 per thousand, and the omega is given. This will give us 1.47 something, the unit. Now, we have momentum plus momentum, angular momentum. Both of them together are equal to this one. The momentum now is conserved, just like always. Now, the direction, all of them in the direction, right? We need to compute the torque. I'll change the color to change the background. Again. The torque, which is the fourth requirement. Any question? Any question online? The torque, as known, it is delta L over delta T, which is the time derivative for the angular momentum. I will not put the direction again because we are working in Z direction. Also, what the torque for what? For what? We don't have any change in the angular momentum. The change in angular momentum is L2 minus L1, which is this minus this will be 0, right? So we don't have a torque. No, I'm talking about another thing. Now, this is the disk, and the ball come here. With the ball come inside this point, the ball act as a normal force, as a friction force. It is a normal force between the ball and the hole. The hole is sticked with the disc. So there is a torque there is a force between the ball and the disc. Can you imagine that? If you jump on a rotating disc, you will see that your legs will go with the direction of that disc because there is a force acting on you. And also, in the same way, you are acting on the disc by another force, which is opposite force. What I needed, it is the torque done or act from the ball on the disc. This torque, the ball will change when the ball come here. It will change the momentum of the disc. It will affect not on so the ball will affect not on the ball, not on itself. It will affect on the other object. So the torque from the ball will change the momentum of the disc. It will not change the momentum of the ball. The disc will change the momentum of the ball. Okay? Because the action and the reaction is between two objects. This is the change in angular momentum over delta T. Okay, I know the change in angular momentum for the disc. I can compute it. But how much the time? Now I gave you the time in that branch, which is delta T. I think it is equal to 0.01 second. In 1 pace a second, the ball jumped in that hole. So the torque from the ball on the disc is equal to that L for the disc later minus L for the disc initial over this time period. Right? If you have any question, please ask. Also online. If you have any question, okay. LD finally, it is this one, 21.15 minus 22.62 over 0.01. This is negative. This is negative because the final momentum is less than the initial momentum. It will be equal to minus 147 newtons meter. We see this number a lot. Now what is happening? Okay. Any questions so far? Now, what is the opposite? The torque from the disc on the ball. It is equal to the change in momentum for the ball over delta T. It is the same time. Okay, which is equal to the change in momentum for the ball. It is the momentum later, which is this one, right? 1047 minus 0. Initially, the momentum initially is 0 over 0.01. This will be equal to the positive 174 Newton meter. This is the torque from the disc on the ball. The force, the torque from the ball on the disc, negative 147. The ball from the disc on the ball is positive 147 because they are applied or satisfy Newton's third law, right? And the negative sign denotes to the direction. So if the positive sign to the z direction, as I told you from before now, the negative sign to the negative z direction. So the torque from ball on the disc is to the negative z direction. and the torque from the disk on the ball is to the positive. Is it understood? Any question online? Okay. What next? Fine. Kinetic energy, yes. Now the kinetic energy before and after. The kinetic energy before, it is equal to the kinetic energy for the disk plus the kinetic energy for the ball, right? How much the kinetic energy for the ball? It is half I omega for the ball, initial square. And this is half I for the disk. This is for the ball. Omega for the disk square. This is the kinetic energy initial. Omega for the ball initially is 0, right? And all of our kinetic energy comes from the disk rotation. Okay, what is the change in kinetic energy for the disk? It is the kinetic energy for the disk later minus the kinetic energy for the disk initial. It is equal to half I. We have the same moment of inertia. Now, omega d before it is 10 rotations. Remember that? Omega for the disk later, it is the same for the ball also. It is 9.35, I think, rotations per second. And ID is 0.36. We can apply that and we can find the change in kinetic energy is equal to negative 89.3 joules. The change in kinetic energy for the disk is negative. Why? Because its velocity later smaller than its velocity initial, right? So its kinetic energy decreased. So this is the change in kinetic energy. So the disk has a kinetic energy and it lose minus sign is losing 89.3 joules. Who gains this kinetic energy? The ball, right? If the ball gains all of this energy, then the kinetic energy is conserved, right? Because the negative kinetic energy from here is equal to the positive kinetic energy here. We will see that. And it will not be correct. It will not be conserved. Okay, the change in kinetic energy for the ball is equal to the kinetic energy for the ball later minus the kinetic energy for the ball initial. The kinetic energy for the ball is equal to half I for the ball, omega 2 squared, which is the same for the disk, minus the kinetic energy for the ball, the rotational kinetic energy. It was 0. Remember that? When we compute this, it will be positive. The change in kinetic energy, negative 89. The change in kinetic energy is positive 43. We have 3 minus that will be 16. We have 46.16 joules are lost. We don't know where are they gone. Go, gone. Who can tell me where is this money? Where is this joule or energy? Who can tell me? When the ball comes inside the hole, there is a sound. When the ball comes inside the hole, there's a heat. What we have also. Who can tell me? Maybe the ball will rotate inside that hole. And this energy comes from this one. Maybe the ball, when it comes to the disc will do like this, right? And this will affect the rotation of the disc on its axis. It will be some friction force here. So we have many places to lose this energy. Okay? Any question about that? Now, the angular momentum is conserved. The kinetic energy is not conserved. So this is a totally inelastic collision, right? And it is a rotational collision or angular collision, not like the previous one, which is a linear collision. Okay. We are done. This is we need to find the work. It is simple. The work done from the disc on the ball is this one. Remember, this is the change in kinetic energy. It is the work done from the disc on the ball. Right? This is the work given from the disc to the ball. Okay? And this is a work done by the interaction, which is from the ball on the disc, which is stored from the disc after going to the ball. Okay. Also, you can see that this is dancer or rotated person when he changed his I, which is the moment of inertia. When he changed its moment of inertia, his kinetic energy also changed. This velocity is slow, but this one is fast, right? That's what mentioned here, and everything is done for today, I think. And I also didn't think that I can finish 11 sheets, but most of them are in example. Any questions so far? Thank you for your patience. Online, any question? Okay, I'll finish the meeting now. I'll put homework later, and I will come with the question.